Welcome back to Chem 4300. In this video, we're going to continue Chapter 19 on magnetism, angular momentum, and spin. Now, what we're interested in this video is to looking at the interaction of the electron magnetic moment with surrounding magnetic fields. And before we get to the electron, though, we're going to just look at some general behavior of magnetic dipole moments in fields. So here's a picture where I have sort of a simple schematic of a dipole moment vector, say a compass needle, which is pinned in the middle here that can pivot, and it's in a uniform magnetic field. Now, we know that there's going to be a force acting on the north end and a force acting on the south end, but if this is a uniform field, then those forces will cancel in a way that there's no translation, but we will see later that there will be some torque that will be acting on this guy. Now, the potential energy for this dipole moment vector in the field is given by minus mu dot b, where mu and b are vector quantities. And you can see if I expand that out in terms of the magnitude of the two vectors and the cosine term there, that when theta is equal to 0, we have the lowest potential energy, which is a stable point here. But when theta is equal to 180 degrees, we have a maximum, so the derivative of the potential is equal to 0, but that's an unstable equilibrium point because that's a maximum there. Now, if we include the kinetic energy, in this case, we're going to write the kinetic energy with just like a rigid rotor here, so since this is going to be pivoting about this point here, we'll have a moment of inertia with the origin here, and we'll have 1/2 I omega squared, some angular velocity, and then we'll have the potential energy term here, which expands out like this. Now, as I said, because of the forces acting on the north and south pole, there'll be a torque on this dipole, and that torque will be given by mu cross b, and that will be a torque that's applied. The torque vector will be along the y direction here. Now, this torque will cause this dipole to move, and if it has a certain total energy, then it will move about with a certain amplitude. And if there's no friction, well, then it would continue to move back and forth because it would just oscillate like a little harmonic oscillator. But generally speaking, if you have a compass needle, you know that it's sort of surrounded by some kind of damping fluid, say just water, that would cause it to stop moving. So when it finally gets to its minimum potential energy, when it's pointing along north, say, then it will stop and stop oscillating because of this damping. Now, let's switch now to thinking about a magnetic dipole moment that's in a magnetic field and has angular momentum on top of having a magnetic dipole moment. So when we think about angular momentum, we think about things like, say, this spinning top here. If this spinning top was in a gravitational field, we know from all of our work on rigid body motion, we know that there will be a torque that will be acting on the center mass of this rigid body, and that torque will cause a change in the angular momentum of this object. So if this object has a total angular momentum and it's spinning with some angular velocity vector, you can work through the equations and you can see that this top will precess around the direction of the gravitational field like this. So this is something I work out in the notes, and you can see how we can derive this precessional motion. But this is an example that you're already familiar with. Everyone has played with spinning tops and know how they precess in a gravitational field. But what I want you to realize is that the same thing will happen if our magnetic dipole moment also had an angular momentum and we placed it in a magnetic field. So let's just say now that we just have a magnetic dipole moment, but now it's spinning about its long axis, and we place it in a magnetic field and we allow it to move. What it will do is, instead of, when that torque acts on this dipole to try to bring it back along the field direction, because it has angular momentum, instead of just moving back, it will now precess around the magnetic field direction in much the same way that the top would precess in a gravitational field. So there'll be a torque that acts on this guy, which is mu cross b, as we saw before, and that torque will cause a change of angular momentum, which will lead to this precession motion. Now, let's go back to the electron. The electron, we saw, will have a magnetic dipole moment that's due to its orbital angular momentum, right? So it has a magnetic dipole moment and it has angular momentum. And if we took our expression for the potential energy for this magnetic dipole moment and took its magnetic moment and put it into this expression, we get the potential energy of that magnetic dipole moment for the electron's orbital motion is given by this expression here. Now, this coupling between the magnetic moment of the electron and the magnetic field is something that's called the Zeeman interaction. So this potential energy term has a name. It's called the Zeeman potential energy term. And if we take the magnetic field to, say, be pointing along the z direction, then this dot product just simplifies to become just Lz times Bz. And so you see that this is our expression for the potential energy of the electron in a magnetic field. So with the magnetic dipole moment from its orbital motion. So what happens then is that in a magnetic field, the electron will lift the degeneracies associated with the m sub L levels. So we saw before for the hydrogen atom that the m sub L levels all were degenerate, but now we see that there is a magnetic dipole moment associated with the orbital motion. And the m sub L levels will now have different energy levels because of this additional term, this Zeeman interaction. Now, let's go back for a moment, back to this classical dipole moment and look at the precession behavior. Now, if we take that torque that's acting on our magnetic dipole moment and we write down this torque in terms of minus gyromagnetic ratio times the angular momentum, then we can do a little rearranging of this expression here, and we can write down that the rate of change of the angular momentum is going to be equal to gamma b cross L. All right. So what I'm going to do is I'm going to define a frequency which is called minus omega L b, which is something we call the Lamore frequency. And what we're going to do is we're going to expand out this cross product for the derivative of the angular momentum, and we're going to get this here. So I'm going to write down the determinant for this cross product, expand it out, and I'll have that expression there. Now, this is going to give us three coupled differential equations for Lx, Ly, and Lz. So I'm going to write them out here, and this is what I have. Three coupled differential equations, except actually one of them is equal to 0, so really only have two coupled differential equations here. So to solve these, I'm going to do a little trick. I'm going to define the L plus and L minus angular momenta components as the complex quantities, which is Lx plus I Ly, and L minus is Lx minus I Ly. And by defining these guys, I can write down that the derivative of dl plus is the derivative of x plus I times the derivative of the y component. And then using these two expressions up here, I can substitute them here, and I get this expression. And then you can see that I can group terms together, and I can see that this gives me minus I omega naught times Lx plus I Ly, and that looks like minus I omega naught L plus, and you can see now I've decoupled the differential equation. So this is very similar to those raising and lowering operators approach that we used before. And similar here, I'll do the same thing with L minus, and you see I get a decoupled equation. So now I have two decoupled differential equations, and I know their solution. They're going to look like this. And so that's the differential equation, and the solutions are going to look like this here. All right. So I've solved the angular momentum as a function of time, and now I can go back to the Cartesian form of these guys, and what you get for the magnetic dipole moment, which is what we're ultimately after, its motion, then we get these expressions here. So this is exactly what we knew would happen before, is that the magnetic dipole moment vector is going to precess around this direction here, the direction of the magnetic field, with a frequency. In this case, it's given by omega naught, which is minus gyromagnetic ratio times the B field. All right. So this is what happens when we take a magnetic dipole moment, and these are with angular momentum, and place it in a magnetic field, and these are what the equations describe the time dependence of that magnetic dipole moment. So next what we're going to do is we're going to look at what happens if you take a magnetic dipole moment and you place it in a non-uniform magnetic field. All the cases we've considered before is just the magnetic field was completely uniform. So this is what I mean by a non-uniform magnetic field, that the field lines are changing, that the density of the field lines are getting tighter at the top and they're looser at the bottom. So this is a magnetic field gradient that's along the z direction here. And so what happens in this case is that the force that's acting on the North Pole and the force that's acting on the South Pole are no longer equal and opposite in direction. So there's not a canceling. So we're still going to get a torque, and we'll talk about that later, but we'll also see that now, in this case, this force is stronger than this force, so this dipole in a magnetic field gradient is going to be pulled up. Okay, that's first important thing to note here. Now, similarly, if I had flipped it around the other way, then you see that the force, the magnetic field is stronger up here than it is down here, so the force pushing down on the South Pole is stronger than the force pushing up. So at this instant in time here, in this particular configuration, the total force will be pushing this magnetic dipole down. All right. And in this case, then we have a situation where the magnetic dipole is perpendicular in this gradient. And so what happens is the force on this North Pole and the force on the South Pole at this in this particular configuration happen to be equal. So there, in this case, there is no net translation of the dipole. All right. Now, generally speaking, for these different cases, we see that this one is going to be pulled up, this one won't be pulled at all, and this one will be pulled down. But we also know that there's going to be a torque acting on these guys. And so if we actually had, a compass needle and we place it in this field, even though it would start to be pushed down, it would quickly be torqued on and reorient and then be pulled back up. So all of these dipoles eventually would get torqued and they would all be pulled up in this particular gradient. But at any instant with this configuration, the force is going to be down here, 0 here, and up there. Now, what we're interested in is magnetic dipole moments that have angular momentum. So that changes that story a bit now, because this guy is still going to be pulled up, but the torque that acts on it is not going to cause it to twist, but it's just going to cause it to precess as it's being pulled up. This guy here is going to precess in the plane here, but it's not going to be pulled up or down because the torque that would have moved it up and caused it to fly up is actually now causing a torque that causes it to precess because it has this angular momentum. Similarly here, this guy is going to have a torque on it, but that torque is only going to cause it to precess. So this guy will continue to fly down in this gradient because the angular momentum is keeping it from being reoriented back. All right. So in this case, compared previously to the previous case, these guys we know would eventually fly up instantaneously. This one's going up, that one's not moving, and that one's being pushed down. But now in this case, we have the behavior where with the angular momentum, that one goes up, that one stays fixed, and that one will continue to go down because the angular momentum prevents it from being torqued and being twisted up. Now, if we take a real example for a magnetic field gradient, so let's take this example for a magnetic field where I'm going to write a gradient along z. So I'm going to have b naught plus g times z. So this is a linear gradient along z. And of course, to make Maxwell's equations requires that this be true, so we have to add this term here in order to satisfy Maxwell's equations, but we'll see later that this part we're going to be able to ignore the effect of that x gradient. But generally speaking then, if we want to calculate the net force on our dipole, then it's going to be the gradient of the potential, and here's the gradient of the potential energy expression, mu dot b. And so for B, we have this expression here, so we'll plug that in for B, and we get this, and then we calculate the gradient of that guy, and we get this expression here. That's the force that's acting on it. So we have a force that's pushing it along Z, and a force that's pushing it along X. Now, don't forget that this is different than our compass needle. We're talking about a moment that has angular momentum here. So for the dipole moment, the z and x components, we're going to plug in our expressions for that precession there so that we have the time dependence into our force. And if I take our expressions for the force with the time-dependent magnetic dipole moment, then I get this expression for the net force at any instant in time. And what we see is that the force along the z direction is time independent, and the force along the x direction is time dependent, but because of the precession motion, it's oscillating back and forth, changing sign. So this guy effectively averages to 0, and the only force acting on our precessing magnetic dipole moment is the force along z, just like I said earlier. So this force will push it along the z direction, and which direction it moves depends upon the orientation of the dipole moment at the time 0. Okay. So as I said, this part will just push it back and forth, but that will average it to 0. So the bottom line here is that this term here will provide us a way to determine what is the orientation of the magnetic dipole moment. If you place a precessing dipole moment, a dipole moment with angular momentum in a magnetic field gradient, then depending on whether it goes up or down or stays stationary, you'll be able to predict what is the z component. So if it's fully up, if the dipole moment is pointing directly along the gradient, then it would go straight up. If it was pointing down, it would go down, and if it was perpendicular, it would stay there, or anything in between, it would have some translation along the z direction depending upon the sign here of the z component. All right. This turns out to be the general idea behind a very classic experiment called the Stern-Gerlach experiment in 1922 that was done on electrons, where we understood that electrons have this orbital angular momentum. So if you wanted to measure the z component of that orbital angular momentum, we know that by measuring the z component of the magnetic dipole moment, we can measure the z component of the orbital angular momentum. So what we're going to do is we're going to exploit this behavior to measure those z components and see what we find in the quantum case compared to what we know would have happened in, say, a classical spinning magnetic top. Okay. So that's it for this video. And the next video, we're going to look in detail at this Stern-Gerlach experiment using these ideas here to understand what happens.